Good morning, everyone. Thank you for the introduction. So I will be talking on the Julia set of Chebyshev method with small degrees. So it is a root finding method, and finding roots of polynomials is a classical problem in mathematical science. Here I will be trying to present a systematic study on this root finding method. Let us see some basic, actually very basics of dynamical system. A rational map is of the form P by Q, where P, Q and polynomials and their co-prime. A point Z hat is said to be fixed if its image is itself, and a fixed point can be classified according to its multiplier. If Z hat is a finite fixed point, then its multiplier is R prime Z hat. And if infinity is a fixed point, then it is defined as G prime 0, where Gz is equal to 1 by R of 1 by Z. Now, the fixed point Z hat is said to be attracting if modulus lambda is less than 1. In a particular case, it is super attracting if it is equal to 0. Z hat is repelling if modulus lambda greater than 1. And if lambda lying on the unit circle, then it is indifferent, particularly. So lambda in this case will be of the form e to the 2 pi I alpha. If alpha is rational, then it is rationally indifferent. And if alpha is irrational number, then it is Z hat is a irrational indifferent fixed point. Root finding methods is a class of rational maps. Basically, it is a function that associates a polynomial P with a rational map Fp in such a way that the roots of P are the attracting fixed point of Fp. Now, the local degree of Fp at each simple root is considered as the order of convergence of the root finding method Fp. There are several root finding methods. In fact, there are several families of root finding method. One of them is conics methods. It is defined with this formula. Note that here n greater or equal to 2 is the order of convergence. And the first member of this family is the Newton method, which is one of the most classical root finding method and broadly studied root finding method. Its dynamics applied to a polynomial is now known. It is basically the work of Sasigura, who proves that if the rational map R is of degree at least 2, if the Julia set of R is disconnected, then it will be having at least 2 weakly repelling fixed point. But for Newton method, there exists exactly one repelling fixed point, which is infinity. So the Julia set of Newton method applied to a polynomial is always connected. The second member of this family is the Hallis method. And actually this family has been systematically studied by Buff and Henriksen. Now we come to our method, Chebyshev method. It is defined by this formula, and it is a third order convergent method. Here P should be of degree at least 2, and it should not be a monomial, because for a linear polynomial or a monomial, Cp is a linear map. The derivative of Chebyshev method is given by this formula, where LPZ is equal to this Pz P double prime Z divided by P prime Z square. So the basic question is, what can be the degree of this rational map Cp? To define the degree of Cp, first we need to define the special critical point. For a polynomial P, a finite critical point is said to be special if it is an inflection point, means second derivative vanishes, but it is not a root of P. For an example, if you consider the unicritical polynomial of degree at least 3, means Z to the power D plus C, where D greater or equal to 3, then 0 is a critical point as well as inflection point, but it is not a root of P. So this is a special critical point. Now, let P be a polynomial having m number of simple roots n number of double root means the multiplicity is 2, and r number of roots having multiplicity greater than 2. Also assume that P has n number of special critical point, then the degree of CP is defined as this: 3 into m plus n plus r plus s minus b minus 2, where b is the total sum of the multiplicities of the special critical points. There are a few information about the degree of CP. So if S is equal to 0, therefore B is equal to 0, then the degree of CP will be 3 into m plus n plus r minus 2. Now, if we consider a generic polynomial, means having no multiple roots, in this case, m plus n plus r equal to d actually. So n equal to 0, r equal to 0. In this case, the degree should be 3d plus s minus b minus 2. So if we consider a generic polynomial without having a special critical point, in this case, degree should be 3d minus 2, and this is the maximal possible degree of CP. If we consider P having exactly 2 roots, that means z minus a whole to power k into z minus b whole to power m, in this case, degree of CP will be 4, and this is the minimal possible degree of CP. In all other case, degree of CP will be greater than or equal to 6. That means we do not have any polynomial P whose degree of the degree of CP is equal to 5. Let us see.
Formula for CP.
This is the formula of CP.
Is there a geometric interpretation of why you should expect the convergence towards this point?
No, actually, I will say it later that it may have some points that may not converge to a root of P also. So,
what's the constant point? So, why do we should converge to the one dimension?
Yeah.
Is the instead for subtracting newtons in sine thing we use containing non-unicritical.
So if we have a polynomial whose critical points are all special, in this scenario, the degree of CP will be this. In a particular case, if we have unicritical polynomial, then degree will be 2d. So actually, we'll be starting Chebyshev method applied to cubic polynomial. In this scenario, degree of CP should be either 4, means P having exactly 2 roots. It may be 6, means for the unicritical case, and it may be degree 7. In this case, the polynomial will be generic. So let us start the dynamical study. For this, we need to characterize the fixed point of CP. So since it is a root finding method, the roots of P will be attracting fixed point of CP, and particularly if a root of P is with the multiplicity k, then it will be a attracting fixed point of CP with this multiplier. So if it is a simple root, then it will be a super attracting fixed point. Infinity is always a repelling fixed point with multiplier this. And so there are finite fixed point of CP which are actually not roots of P. This type of fixed point are known as extraneous fixed point, and CP has extraneous fixed point. These are precisely the solution of LPZ equal to -2, and their multiplier is defined by this formula 2 into LP prime zeta, where zeta is an extraneous fixed point, and LP prime is P prime P triple prime divided by P double prime square. And the interesting thing is, this extraneous fixed point zeta can be any of the kind. It may be attracting, may be repelling, may be indifferent. Actually, this property makes the Chebyshev method special comparatively other root finding methods like conics. In conics method, all the extraneous fixed points are repelling. And the problem is, if suppose we have an attracting extraneous fixed points, then it will having a basin of attraction. So you may have a point that will converge to a number, to a point which is actually not a root of P. So in this scenario, the motivation of root finding method fails. The motivation of root finding method, so we have a initial guess, we will iterate it, and we will be expecting that this iteration will converge to a root of the polynomial P. But in this case, the Chebyshev method may not give the root of P. Means the motivation of root finding method may fail here. Chebyshev method also satisfies a special property known as scaling theorem. Suppose we have a polynomial P. Now post conjugated affine map TZ is equal to AZ plus B with this P, means P composed T. Now multiply a constant of lambda. So construct a new polynomial G which is equal to lambda PT. Then the Chebyshev method of P and Chebyshev method of G, they are conjugate and they are affine conjugate with the same affine map T. Not only the Chebyshev method, that this class, Chebyshev-Hallis family, as well as conics method, as well as basic family, they all satisfy the scaling theorem. And the beauty of scaling theorem is it gives us ample amount of simplification to consider the polynomial. Now we start the study of cubic polynomials. We start the study of CP applied to cubic polynomials. In the first case, we consider the unicritical polynomial. Then we prove that if we consider an unicritical polynomial, its Chebyshev method will be conjugate to this rational map. Actually, this rational map is the Chebyshev method applied to Z cube minus 1. Here is the application of scaling theorem. We may have several unicritical points, but these several unicritical points, I can represent them by a single unicritical polynomial Z cube minus 1, and all the Chebyshev method applied to unicritical polynomials can be conjugated with this rational map, and we found that its Julia set will be connected. Similarly, if we consider the polynomial, cubic polynomial, of course, having exactly two roots, Z minus A whole square into Z minus B. Of course, A not equal to B. In this case, we can prove that the Chebyshev method will be conjugate to this rational map. Actually, this rational map is a Chebyshev method applied to this polynomial, Z minus 1 whole square into Z plus 2. And we found it that its Julia set will also be connected.
What do you mean by being non-generic?
Not generic means all roots of P may not be simple, may have a multiple root. So in cubic case, if a root is multiple, then only possibility of that polynomial will be of this form, z minus a whole square into z minus b. Here a is the multiple root. So here are the picture. This is the picture of CP applied to unicritical case, and this is applied to exactly two root case. Now we parameterize the family of polynomials. Actually, now since we have learned about the unicritical case and exactly two root case, now we consider polynomial is generic, means no multiple root as well as it is not unicritical. So in this case, for any lambda, if the Chebyshev method having an extraneous fixed point with multiplier lambda, then this Chebyshev method will be conjugate to the Chebyshev method applied to this polynomial. So the parameter lambda is actually the multiplier of an extraneous fixed point of CP, the Chebyshev method applied to P. Actually, there are several parameterization. One of the well studied parameter is this parameter, lambda minus 1 z minus lambda, where lambda belongs to C. And also these parameters is also being studied, but for our case it is more profitable because from this parameter we will be getting an idea about an extraneous fixed point of CP, and we are removing these two possibilities because for unicritical case the multiplier of all extraneous fixed point is actually 5, and there is no Chebyshev method whose extraneous fixed point will be having multiplier 6. So apart from 5 and 6, the polynomial can be made, and any Chebyshev method having an extraneous fixed point with this multiplier can be conjugated to C lambda, which is the Chebyshev method applied to this polynomial. So considering the constant term of this polynomial as high lambda, we have this form of this of the Chebyshev method, and its multiplier, its derivative will be this. So from this derivative, we are getting that the roots of P are actually super attracting fixed point of CP. The roots of P are critical point. So we have already seen that it will be also a fixed point. So they are actually super attracting fixed points, and the poles plus minus I are also critical points. And apart from this, there are two critical points, 1 by root over 5, which are simple. Degree of C lambda is 7. So we'll having 8 number of fixed point. So there are 3 from the polynomial. 1 is infinity. So there will be 4 more fixed points, which are going to be an extraneous fixed point of C lambda. Now, this minus 1 by root over 5 minus lambda, this is a fixed point with multiplier lambda. And other fixed points will be the solution of this cubic equation. Now consider the parameter within the interval minus 1 to 1. So we are going to consider extraneous fixed point either attracting or parabolic. In this case, the coefficient of the polynomial are all real. Actually, it will be having exactly one real root, say R lambda, and 2 complex conjugate roots, Z0 and Z0 bar. And the extraneous fixed point xi lambda is also be real. If lambda is in between minus 1 closed and open 1, in this case, apart from xi lambda, there will be 3 more extraneous fixed point. 1 will be real, namely alpha lambda, and 2 complex conjugate. But if lambda equal to 1, that means the fixed point is multiple. So for a multiple fixed point, the multiplier is always equal to 1. In this case, xi lambda will be equal to alpha lambda, and there will be two more complex conjugate extraneous fixed points. So we'll see the real dynamics. So on the real line, there will be r lambda as well as xi lambda. So r lambda is super attracting fixed point of c lambda, and xi lambda will be either attracting or parabolic. There are two critical points on the real axis, plus 1 by root over 5, minus 1 by root over 5, and we can prove that this minus 1 by root over 5 will be lying on the basin of attraction. In fact, on the immediate basin of xi lambda, 1 by root over 5, this critical point will be lying on the basin of attraction, not in the immediate basin of r lambda. So this immediate basin of xi lambda will be containing exactly one critical point. So it will be simply connected, as well as the immediate basin of r lambda, it will also be simply connected, and the line segment from infinity to r lambda. So this interval will be lying inside the immediate basin of r lambda. That means the immediate basin of r lambda is unbounded, and the poles, both the poles, will be lying on the boundary of r lambda, immediate basin of r lambda. Here is the graph. We have considered lambda equal to -1, 0, and 1. So this is the graph. So in this means from infinity to r lambda, if we consider any point, that will converge to gradually converging to r lambda. Similar for C0 and C1.
So do you have a parabolic point of?
Yes. For C lambda, that the xi lambda is parabolic. Even this case C minus 1, xi lambda is parabolic. So the whole dynamics, the immediate basin of Z0 and Z0 bar, these two also will be simply connected. The other extraneous fixed point apart from xi lambda will be repelling. The Fatau set consists of the basin of attraction of these four attracting or parabolic fixed point. Julia set is connected. In fact, if we consider this set, the forward orbit of critical points, then the closure of this set union the Julia set is actually finite in this case. So this type of rational maps are called geometrically finite rational map. So our C lambda is in fact a geometrically finite rational map. And for a geometrically finite rational map, if the Julia set is connected, then it is locally connected. So in our case, C lambda is a locally connected, C lambda will be having a locally connected Julia set. Yes, ma'am.
What is the intuition of why the Julia set is connected? So how do you do this, or just an idea?
So basically, we have these two free critical points whose forward orbit is to be investigated. Apart from other critical points, the roots of P already in the immediate basin, poles are on the Julia set since infinity is a repelling fixed point. So now we have investigated that -1 by root over 5, this will be on the immediate basin of xi lambda, and 1 by root over 5 will be in the basin of attraction, not in immediate basin of r lambda. So the immediate basin are containing exactly one critical point. So by Bocher coordinate theorem, we can prove that the immediate basin Bocher coordinate. So immediate basins are simply connected, and we do not have any other basin of attraction apart from this. So Fatau set containing the immediate, basin of attraction, all are simply connected. So the Julia set is connected.
Sorry, so for real maps, everything converges to one of the two.
Yes. So these are the figure. We have taken parabolic extraneous fixed point lambda equal to -1. The right hand side is a picture of the immediate basin of xi of -1. Second picture is for lambda equal to 0, and third picture is for lambda equal to 1. Means here lambda is a xi lambda is a multiple fixed point. There are some remarks and future direction we can proceed further. If we consider lambda is less than 5, then psi lambda is a real map. Its graph is this graph. So we will be having a delta lying the right hand side of 1 such that psi of -1 is equal to psi of delta. In this case, if we consider any lambda tilde from this interval, then psi of lambda is equal to psi lambda tilde. That means p lambda is equal to p lambda tilde. In this case, the Chebyshev method are same. Actually, what is happening? We will be having another more real extraneous fixed point alpha lambda. So if we consider any lambda from this interval, xi lambda will be repelling, but in this case, alpha lambda will be attracting. So we can extend our domain from -1 to 1 to -1 to delta. In this case, the Julia set of C lambda will be connected. This is an observation. Here is a question that apart from that interval -1 to delta, what Chebyshev method can be? That means in this case, the coefficient of C lambda are all real. So the Julia set will be symmetric about the x-axis, and the free critical point ±1 by √5 are also real. Its forward orbit will be also real. So in this case, the Harman ring cannot be possible. But we do not know what will be the Julia set. Still, it will be. So I am expecting that the Julia set will be connected here also. But analytically, I cannot able to prove that still now. Even another question, if we consider lambda from the unit disk, so I'm excluding the real part. So lambda is something on the unit disk. In this case also, xi lambda will be an attracting fixed point. So its basin of attraction will be having a critical point. So one of the free critical points will be lying on the immediate basin of xi lambda, and one is free. So here also the Harman ring is not possible, but we do not know what will be the Julia set. These are the references. This talk has been taken from this paper. Thank you for your kindness.
Are there any questions? Do you always have a root that is attracting? Could it happen that maybe all the roots are repelling points for
Roots means
you start with a polynomial key, right? And you look at the roots, the zeros. And to iterate key to find zero.
Yes.
Could it be that they're all repelling?
If we consider a root of P, then it is always attracting. This is a property of root finding methods.
Oh, but then you have this extraneous.
But for Chebyshev's case, apart from roots, there are some finite fixed points which are not the roots of P, and it may be anything.
Oh, I see. Okay.
Actually, for your question, if we consider the Newton method or any conics method, means any member from the conics method,
Right.
here actually the roots of P are precisely the attracting or super attracting fixed point of that method, and there is no fixed point which is attracting or super attracting. All the external fixed point are repelling for that case, but here it is not.
Any more questions? If not, let's thank our speaker again.
I have finished little earlier.